All right, so for our physics project, we're solving for Peyton's acceleration in an elevator. How is this done? That's a great question. What we're gonna do is put a scale in an elevator, and we're going to see the change in normal force as the elevator accelerates.
For our project, we used the dynamics and kinematics lens to calculate the acceleration of me in the elevator and my constant speed. We could have looked at the energy lens or the momentum lens, and through energy we would have seen when going down, the gravitational potential energy would turn into kinetic energy and the work the elevator does, and going up, the work the elevator does would turn into gravitational potential energy and kinetic energy. And my momentum is not conserved because there are outside forces acting on my body.
Alright guys, so Peyton's mass is 62.414 kilograms. Therefore the force of gravity is that, the mass, multiply the acceleration, gravity, which is 1g10. So it's going to be 624.14 newtons. So we are going to analyze this situation, or analyze Peyton and the normal force acting upon her as the elevator goes up and as the elevator goes down. Starting with the elevator going up, the velocity and the acceleration are both in the upwards direction, and we can see that the normal force is obviously going up because it's going to be opposite to the force of gravity, and we can see that because it's going up, normal force must be greater than the force of gravity, therefore the acceleration is in the upward direction. We can also see this algebraically, but similarly, when we're going down, we have the force of gravity acting downward, and we have the normal force is still going up, but we will be able to tell the normal force is much less in this situation because we are accelerating downward, as you can see.
And it's important to note in most situations, the positive direction is defined by the direction of velocity. Okay, so for situation 1, the velocity and acceleration are both upwards. So we found the scale reading in the elevator as the acceleration is happening to be 147.2 pounds, which we converted to kilograms to 66.77 kilograms. We found the force normal by multiplying that by 10 meters per second squared to get 667.7 newtons. And then we plugged that into our equation for acceleration that we found in the other, that we had found earlier, and we found that acceleration as the elevator is going upwards is 0.698 meters per second squared. So now we're going to go over situation 2, where the velocity and acceleration are both downward. So for situation 2, we found that the scale reading was 127 pounds, which is 57.6 kilograms. We multiplied that by 10 meters per second to get the force normal is 576 newtons. And then we found acceleration is equal to force of gravity minus the force normal over mass, and that equals 0.769 meters per second in the downward direction.
Now we're gonna use kinematics to find the constant velocity of the elevator as it goes up. Her time spent accelerating was only 0.74 seconds. And we know that acceleration equals the change in velocity over the change in time, and since she's starting from rest, then V naught is 0. So basically we take V final, or her constant velocity, and have that equal to acceleration times the change in time. And we found the acceleration earlier was 0.698 meters per second squared, which you multiply by 0.74, which we just found. And then the constant velocity is 0.516 meters per second. 2.3 seconds as she's going down. So we do the same thing. We have acceleration equal to change in velocity over change in time. Set that to velocity equals acceleration times the change in time. And so we have V final equal to 0.769 meters per second squared times the 2.3 seconds it takes. And we have that equal to 1.769. So as you can see, the time spent accelerating downwards is more than the time spent accelerating upwards. Therefore, the velocity travels down is much higher.
Okay, so now we're going to talk about some possible errors we may have made. Our first one is the scale timing. So stepping on and off the scale as the acceleration of the elevator started might have been a little bit off. And then our second one is the correlation between the timer and the scale. Since we had to start both the timer and the scale and press the buttons of the elevator all at the same time, the timing of that may be slightly off.